We present BSP-Net, a network that generates compact meshes via binary space partitioning. Recently, several methods have been proposed to represent 3D shapes within neural networks. These approaches mainly fall into two categories. One is to warp a template mesh into a target shape. Another is to represent geometry via implicit functions. However, implicit methods require matching cubes to extract the surface mesh. The extracted meshes are not compact and contain too many polygons. In this example, we show a 3D object generated by MNet. The mesh is obtained by running matching cubes at a resolution of 256, and it contains hundreds of thousands of vertices and triangles. We would prefer to have a compact output mesh with a few hundred vertices, and retain the ability to represent complex structures. To address these problems, we propose a neural network which outputs meshes natively. Our generated meshes are low poly and guaranteed to be watertight. The edges can reproduce sharp details, yet can still approximate curved boundaries. Overall, we attain high visual quality with very few primitives, as reflected by the wireframe. Our key idea is derived from binary space partitioning trees. Given a set of oriented planes, and the connections to group them, we can compute the intersection within each group to obtain convex shapes, and then take their union to construct the final output. The entire process is based on CSG operations, hence the output shape is a polygonal mesh. We designed the network in such a way that each component represents a part of the BSP tree. Given a voxel model or an image as input, we use an encoder to get the corresponding feature code, and then use an MRP to map the feature code to plane parameters. The planes are the leaf nodes in the BSP tree. Similar to the training of other implicit models, we sample a set of points in space. The product of the plane parameters and the point coordinates will give us the sign distances, which are visualized in the first layer of the right figure. To represent the connections in the BSP tree, we employ a trainable binary matrix. The product of this matrix with the distances represents convex shapes. Finally, we introduce some auxiliary weights, and use the weighted sum to approximate the mean pooling operation, or use mean pooling directly to obtain the final output shape. Here, we visualize the training process for a 2D toy example. We initialize the network with random weights before training, including the binary matrix that connects planes to convexes, and the auxiliary weights that aggregate the convexes to form the output. All weights are float numbers, so that the gradients can easily propagate. In stage 1, we train the network with reconstruction loss, and 2 other losses to help structure the tree. Note how the connections are changed in the bottom level. The first stage gives a reconstruction of the target shape, but it might not be accurate due to the continuous weights. Therefore, in the second stage, we binarize the connection weights via thresholding, and replace the weighted sum with mean pooling. Here, we show the input shapes in our 2D toy experiment. The task of the network is to reconstruct each image as a combination of convex parts. And here are the outputs. Since all shapes share the same set of convexes and tree connections, we find shape segmentations and correspondences in the convex level. Here, we show that the nth convex consistently represents the same part. We compare our method with several other methods that perform shape decomposition via reconstruction. Our method not only achieves better reconstruction quality, but also has better segmentation results. Similar to the 2D case, we can find natural correspondences between convexes. Here, we manually group convexes into semantic parts, and visualize correspondences using different colors. Finally, since our BSP-Net is a differentiable 3D decoder, we can easily pair it with an image encoder to achieve single-view reconstruction. We compare with several state-of-the-art methods to show the representation ability of our network and the compactness of the outputs. Please pay attention to the close-ups of mesh tessellations in the middle. Our method achieves comparable performance to the state-of-the-arts while using fewer amount of vertices and triangles. There is a recent work, CvxNet, that also performs convex decomposition. Our method differs from theirs as we target low-poly reconstruction, and our network has a dynamic number of convexes for different shapes. The source code of our work is available on GitHub. Thank you for watching.